Fully derived about. I see. But there you that's what happens. Oh, yeah. So it's like yeah.
Everyone, thanks for coming to the special quantum theory seminar. Today we have the pleasure of hosting Xiaomi, who was an undergrad here at Cornell, and he's now at Google Research. He's going to tell us a little bit about what can be done with quantum processors.
All right. All right, thanks, Omri, for the introduction, and thanks to Una for inviting me here. Actually, to begin with, can people hear me okay? Okay, perfect. Yeah, so it's, as Omri mentioned, I was an undergraduate here, 13 years back. So I left, I think, 2013. So it's very nice to be back on campus and see a lot of familiar faces. When I was undergraduate, I was pretty much in the basement, in the machine shop all the time, actually. John passed me a lot of drawings and I make them. We work with the old fridge. So it's a very fond memory for me. And, again, I was really excited to be back. But what I'll be talking about is entirely different from what I did as an undergraduate. Yeah, hopefully still cool. I wasn't quite sure what the audience would be, so I kind of prepare a mixture of several topics. So step through them. If there's something you want to ask more about, feel free to slow down. We can sort of talk through them. We don't have to get through all of the materials. I would rather that we talk about things that interest people. All right. Okay, so the overall theme. Nowadays I'm at Google, so I kind of manage a group of people, research scientists whose essential mission is to accomplish some sort of beyond classical quantum advantage type of experiments with near-term and eventually fault-tolerant quantum devices. And this is our entire team, which is huge these days. This is not even the entirety of it. I think we have maybe 300 people by now. Most of the experimentalists work off Santa Barbara. In LAX, we have some theorists working there. And then in Seattle, we have some software engineers. But the entire effort is more or less based in Santa Barbara. Once a year, we kind of gather around one of these nice offices and just take pictures and drink. So this is, I think, 2 years ago. Okay, so to begin with, let me kind of flesh out what the company or the group's mission is and where we fit in. So roughly speaking, there are maybe 3 parallel threads that we're trying to accomplish with this kind of effort at Google. The first and most important thread is system engineering. We have to scale up the system, continue to increase or reduce error rates for the qubits, so we can sort of march from a handful of physical qubits to 1 error-corrected qubits with errors, let's say, in the 10 to the minus 6 range. And this is hopefully comes into fruition in the near term, and then eventually march to a handful of logical qubits and more. So this is a very much hardware-focused thread, and all of us contribute to that thread. Now, in parallel to that, and this is the focus of what I'll be talking about, is an application thread, right? A thread. As we march in our hardware development, we also need to understand what kind of quantum algorithms or applications are most suited for different evolution stages of these hardware. Roughly speaking, right, we're still in this NISQ era where we're not trying to use logical qubits because they're just not as good as physical qubits yet. Mostly, we're trying to use good physical qubits to do something. So here, we're hoping to identify at least 1 and hopefully more cases where we can do a quantum algorithm that is useful for something. And we'll debate and define what useful might mean. And eventually, once we kind of hit a handful of logical qubits, that's a place our team will transition into fault-tolerant algorithms. Fault-tolerant algorithms. Okay, so now along that thread, I'll kind of cover 3 things. So I'll give a brief introduction of what superconducting qubits are, how we build devices out of these tools. Probably familiar with quite a few people here now. I talked to you guys, and I know there's actually a substantial superconducting circuit effort going on here. So I'm going to go through that relatively quickly. Then I will spend quite a bit of time on a couple of experiments where we demonstrated some elements of quantum advantage and try to move those demonstrations into somewhere we hope that will be useful actually for some sort of scientific purpose. And then the last one, which is about one particular experiment where we move away from this somewhat contrived problems where we can demonstrate quantum advantage to a problem where it's not yet quantum advantage, but holds a lot of relevance to physics and things that we find exciting, right? Okay. So let's talk about superconducting circuits and why these things are cool toolboxes to build quantum processor with. They're very useful because they're quite simple. This is for qubits, you want to work with something that's as easy to control, as easy to fabricate as you can. And this is where superconducting, or specifically transmon qubits, come in. So what these things are essentially is a nonlinear LC oscillator. So you can sort of draw a circuit diagram that looks like this. So it's a charging energy, so a capacitor that defines it, EC, and then there is a squid loop that sort of defines a tunable inductor, and also a nonlinear one. So if we look at the Hamiltonian of this nonlinear circuit, it looks like this. So you have a linear charging term, and then you have a cosine potential that defines the flux operator. So these things can be thought as essentially, positional momentum operators, like a linear oscillator, except here the cosine term make it somewhat nonlinear. And these are micrographs of what these circuit elements look like. So typically capacitors, we can use a cross, for instance, to define these things. And this line drives delivers the microwave signal that drives the qubit rotations. And the nonlinear inductors are typically much smaller. So here is the micrograph for a squid loop. So if you look at these little arms of metal, they kind of overlap in a very small area, and that little area is oxidized, and that defines the tunnel junctions making up of the squid loop. Okay, so now, so why can you use this as qubits? Well, for a linear oscillator, you certainly cannot, because all of the states are separated by equal frequency. But by introducing this nonlinear element and have the cosine potential, the energy states are separated by a non-equal spacings, right? Basically, you have a fundamental frequency going from the 0 to 1 state, and then the successive states are separated less and less in frequency by amount eta. So this is what we typically call anharmonicity. Give you a sense of energy scales, these omega naughts, these fundamental frequencies are typically in the range, let's say 4 to 6 gigahertz. And the etas are typically in the range of 200 to 300 megahertz. So you have about 5% fractional nonlinearity. And these are enough to separate out the states, so we can control transitions individually, but also small enough to suppress a lot of things like charge noise that you would otherwise encounter if you don't have the capacitor. Over the years, we found as simple as these things are, they're really effective. And this is why we chose to kind of build qubits, large processors out of these things. In terms of control, single qubit gates nowadays are fairly straightforward. So what you do is you kind of drive the system with a microwave burst, and that creates rotations in the 0 to 1 state. And you have to be careful with the shaping of these things, but typically you can suppress leakage to higher states. And gate fidelity approaching 4 nines are becoming a possibility with the single qubit gates, even with transmon qubits. Readout is also relatively straightforward. So what you do is you have a linear oscillator defined by a readout resonator, and then you kind of couple that to the qubit. And depending on the qubit is pointing up or down, it induces a different dispersive shift on the frequency of this readout resonator. And then you can demodulate that signal and read out the qubit state. And this is usually quite non-invasive, although there are transitions we're trying to suppress, but generally you do a good job, and you can get fidelities in the 2 nines easily these days. Okay, what does sort of take a lot of thought, and this is usually the Achilles heel of quantum computing, is 2 qubit gates, right? These are the things that generate entanglement, and they're typically the hardest to do. So our approach, which we hope that can take us quite far, is making everything tunable. So in our qubits, not only are the frequencies tunable, but the couplers are tunable too. So this is a simplified schematic showing what the tunable coupler is doing. It's kind of silly. So let me just describe to you in words what these are. So the tunable coupler is essentially another transmon qubit placed at much higher frequency. What it does is it kind of has a dispersive induces a dispersive shift on each qubit. At the same time, there's a second order coupling between the qubits that get turned on, which is roughly the same as a dispersive shift from the coupler to the qubit. So if you write down the Hamiltonian of this coupled system, you have something basically look like this. There's a individual qubit terms, and then there's a coupling term which is written out here on the right if you decompose it into a computational basis. So here what you have is a transverse interaction xs plus yy and a longitudinal interaction. So this is a very clean Hamiltonian, right? For condensed matter, for many-body theorists, this is called the Heisenberg SAZ model. And nicely, you can sort of also change the amount of ZZ interaction compared to XXY interaction, because you can see that prefactor of these things are very different. Where the ZZ interaction is actually a second order effect. So you can usually tune the relative strength of these terms. Now, what this gives you in terms of flexibility is that you can use baseband control, and by doing a single pulse, you can engineer a family of different 2-qubit gates. So this is some experimental data where you deliver a pulse that brings the qubits, let's say the fundamental frequency of the 2 qubits together, and then turn on the coupling, wait for some time, ramping it back down. And if you sweep, let's say, the maximum coupling between the qubits, Gmax, and the length of this pulse, let's say TP, you get, and then do some tomography on the resulting state, you get a map of swap angle, theta, and conditional phase that look like this. So essentially, you have a series of fringes corresponding to swapping and swapping back of the qubits. And at the same time, the ZZ just accumulate monotonically in the diagonal direction. And now you can sort of go to your computer, do a simple 2D optimization, and tell yourself where you're supposed to go in terms of pulse length or coupling in order to hit a specific combination of theta and phi. So these gates, the combination of these two gates is called FSIM gate. It's very useful because we can do a lot of quantum algorithm with these things. And for the majority of the combinations, we can hit gate fidelity nowadays from 99.7 to almost 3 nines. So yeah, so this is how we build our 2-qubit gates. And again, we like it because it's very simple. It's just one single pulse. And typically with gates, the simpler the control scheme is, the less of an error channel you'll be dealing with. Okay, so that's a primer on transmon qubits. Now let me move on to something more kind of many-body physics sort of domain, which is asking ourselves, let's say you have 50 or 100 of these things, what are the meaningful experiments you can do that the classical computers cannot? So this is where things become a little bit interesting, because you have two approaches, right? And I was talking to Eric and Lance about this. You can sort of take interesting proposals, run them, and most likely you probably find that you're limited in circuit depth and things will be easy. Or you can sort of engineer problems that are classically hard at the given moment and hope to kind of evolve this eventually into something that is both physically interesting and hard. We're taking both directions. So what I'll be covering is the second option, which is taking, engineering a problem that is hard and try to gradually evolve that into a physically interesting system. So if we kind of follow that train of thought, then the first question you ask is, what kind of dynamics is classically hard? Well, the answer is, well, it has to be non-integrable. So as we know that in classical physics, there are two kind of dynamics. Is integrable, where you kind of system at some point, there's a lot of conserved quantities. And then there's a case of non-integrable systems where the system essentially explores all points on the phase space over time. And the non-integrable cases tend to be classically hard. That, in generic cases, you have exponentially rising computational costs to compute these things. So that's one crucial ingredient we have to put into this problem right now in order to it to be even conceivably hard on near-term devices. What else do we need? So let's kind of now follow that train of thought and then engineer a quantum circuit that sort of delivers the maximum amount of non-integrability in a short time. So that the answer to that is basically random circuits. So this is a typical random circuit that we like to run in the lab, which is a circuit like this, where you randomize the single qubits with a pi over 2 pulse along a random axis, and then you do a pairwise I-swap-like gates. So these are essentially the maximally entangling 2-qubit gates there are, and then you repeat this many times over. And the system tend to converge to a chaotic limit very fast, and therefore we kind of choose this as a toy model to study, or rather to compare with classical simulation. Okay, so this is the first ingredient. You need some sort of circuit that generates a lot of entanglement and cause a lot of chaos in a short time. But then you still have to characterize the circuit, right? And this is where things become really tricky. So the first thing the initial thing we tried is essentially looking at the wave function directly by sampling from it. So here is a set of probability that we can measure. I think this is, 12-qubit systems. You have roughly 4,000 something amplitudes. So one thing you can do is just collect a lot of bit strings and then plot out the probabilities of each individual bit string. So here, why is this kind of interesting thing to see is because there's a very strong differentiation between, let's say, a broken quantum processor where it just spits out random outcomes, then every bit string is equally likely, or a very coherent and quantum chaotic wave function, which give you something called a Porter-Thomas distribution. That's these kind of blue spikes underneath all this. So this very spiky distribution is a signature that you have a very coherent wave function that is at the same time classically complex, because chaotic wave functions are just hard to approximate exactly using classical methods. And experimentally, what you do is you kind of measure these things and compare against these two limits, the broken limit and the coherent but chaotic limit. Typically, you see a landscape which is somewhere in between. So these orange dots are the ones that you kind of measured experimentally. So by comparing this distribution that you obtain experimentally with theoretical numerical simulations, you can actually obtain a fidelity of overall wave function. And then what you then do is to sort of extrapolate that fidelity to a large system limit and ask yourself how much it costs to sample such bit strings using, let's say, tensor networks methods, and then compare that to the simulation time you need on the quantum device and see whether you can sort of beat the classical computation that way. And I think most of you know that this is essentially successful. Back in 2019, we published the first quantum, well, at the time it was called quantum supremacy paper. Nowadays, we like to call it beyond classical sampling for various reasons. So there, of course, one thing that's kind of interesting to see is that many groups have tried to replicate this, and a lot of groups in China, for instance, and we ourselves have done this 3 times. So we did it back then, we did it in 2024, and then in 2025. And you can really see that the computational cost is rising exponentially over time, right? So back, I don't know, in 2019, it takes us, at time, I think Summit was the most powerful supercomputer at the time. So with the tensor contraction protocol that we have at the time, it takes about 1 million years. So actually nowadays, the tensor contraction can simulate this on a GPU. So this is no longer beyond classical. But nevertheless, because our quantum processor is growing in size, it doubled from back then to now, and the fidelity almost quadrupled. So we can run a lot more qubits with a lot more cycles. So despite the improvement in classical methods or simulation protocols, we managed to stay ahead of the curve and keep pulling this difference. And nowadays, the most recent experiment takes 10 to the 25th year some frontier. I mean, no one would ever try to do this, but but it is something that is very dramatic.
We've been to get the exact result, but one of the achievements they found in the earlier cases was you only need to simulate up to the noise level you had on your machine. It wasn't quite that hard.
That is not quite entirely accurate. I think there is basically a phase transition. In fact, I was studying this paper here. So your system has to cross a certain fidelity threshold. So below this fidelity threshold, there's a way to spoof your result because your system is essentially broken up into unentangled patches. But what we show here is there's actually a fidelity transition. So once your fidelities go beyond a certain limit, you have full entanglement across the entire system. And this spoofing protocol just drops so quickly across this threshold that as long as you're staying in the good side of phase transition, you're good to go. And this is what we established here. So we, in fact, for all of the following experiments, we always check whether we're on the right side of phase transition or the other side. Yeah.
So you think, that was excellent to know. And
right.
So we should not expect somebody to come up with a new protocol on GPUs that will cut significantly into this.
Not for sampling problems. Yeah, I mean, the gap is so large these days that it's somewhat inconceivable that someone can be so smart with tensor contractions that suddenly close this at these. Yeah. Okay. But this is, again, after all, remains a sampling problem. Apart from sort of demonstrating you can do something that is hard, it's really not quite useful, right? So we all acknowledge that. So then you kind of ask, what are the crucial ingredients into a quantum algorithm that allow you to actually do something more practical? Roughly speaking, there are 3 things that need to happen. I mean, first of all, you need the classical computing sort of complexity to go exponential in time or some sort of volume, whereas your quantum complexity should only go polynomial. This is satisfied by random circuit sampling. What is not satisfied is two other things, right? First of all, your outcome has to be verifiable. You cannot sample once and you never see the same bit stream twice, which is really what happens in large Hilbert space. You never see the same bit stream twice. It's hard to think how you would make use of that. So what this suggests that you have to look at expectation values of some sort, something that can reproducibly measure and never changes. At the same time, these expectation values has to tell you something about the quantum system that can be used in a practical setting. So these are the two requirements that kind of surfaced after the random circuit sampling stuff that we try to now think, how can we engineer a problem that kind of start to march ourselves closer to these two other requirements. Okay, so let's see how can we do these things. So once you start thinking about expectation values and also thinking about chaotic dynamics, you're kind of faced with a very bad issue. So as probably all of you know, the expectation values basically shrink exponentially in the generic ergodic setting, right? Because chaos basically thermalized the local systems. They spread into the whole wave function, and you get nothing to measure locally. And this is seen in many experiments. I think the first two are about Bose-Hubbard models, maybe not even the last one. I think you can see that in all these systems, you see some interesting features or signals at the beginning, but over time they all get washed out. Most of them are due to intrinsic thermalization, some of them are due to noise, but you're faced with this kind of problem. So typically, the system becomes featureless or zero before you have a chance to beat classical computation. So this is kind of the issue we immediately face when we try to move away from bit stream sampling, which is always guaranteed to give you an XV fidelity of 1, to something which is local. So it thermalizes and goes to 0. So how do we evade this kind of quandary? Well, that thing about what thermalization does, right? I mean, as an experimentalist, my kind of naive interpretation of thermalization is always some sort of decoherence process. Local qubit gets spread to the rest of the environment. You never see anything again. So, well, experimentally, how do you reverse this decoherence process? We know that echo is very effective. So the natural thing, as experimentalists to try, although there are also theoretical reasons to do it, is to basically evolve system forward, backward, several times. But that seems boring because if you evolve forward and backward, you get 1, right? It's trivial. You just get return. So the next thing you want to introduce is some sort of perturbation in between the forward and backward evolution. So these are these kind of B operators. So now you put together a circuit like this. It basically looks like a series of U and U daggers. So these are many-body operations that go forward and backward. And in between, there's perturbations in, let's say, 1 qubit. As many of you know, this thing has a formal name. It's called out-of-time order correlators. And this can be it can be first order, where you just go forward, backward once. And then you can also choose to do it several times over. So the idea is that maybe by reversing the time or partially reversing time repeatedly, we can refocus the signal to a good extent and get away from this kind of exponential decay of local observables that we're dealing with. At the same time, and this is a kind of learn after the experimental facts, I'm putting it in between before the experimental results, but I'm just going to tell you the insight so you kind of see where we're going. Because the forward and backward evolution, there's actually a way for polystrings to kind of interfere in this process. And actually, these processes tend to be constructive. So because there's an interference effect that covers the entire Hilbert space, the classical methods really struggle against capturing these local observables. Again, this is just an observation after effects. I'm just telling you that, and hopefully that surfaces in the data soon enough. So these are kind of the grand motivations that sort of motivate us to do this experiment. And then Michel Deveray joined us, and we talked to him, and he offered a paper, which I was not aware of, maybe out of ignorance, but this kind of has a time order tradition in MR systems, right? The first Loschmann echo experiment done, I don't know, 40 years ago, are exactly using this kind of trick to restore sensitivities to the underlying dynamics. So we're, in some sense, doing something that has already been done in some other experimental systems many years back. Okay, so let's now look at some data on these OTOGs and see how they behave and why they're kind of different from time order correlation functions that you typically measure in a quantum simulator. So here is what I'm doing is I'm looking at a lattice of qubits, and I'm applying this kind of perturbation in 1 qubit somewhere in the lattice, and then measuring it at a different location somewhere else on the chip. So what I'm plotting here is the behavior of first order OTOG over time. average over a lot of random circuit instances. So here you see a nice trend where it basically stays at 1 until there's a certain time where it suddenly drops to close to 0 on average, right? This is because it takes some time for information to propagate from where I perturbed it, this B, to the measurement operator M. Before that happened, the two operators essentially commute. So you're measuring 1. And afterwards, they start to become non-commuting, and then you get some OTOG, which is non-zero, close to 0 and non-unity. So average behavior is kind of nice, but also a little bit boring in the sense that it just drops to 0 very quickly. But what was striking to us when we first did this experiment some years back is that there's an underlying fluctuation, between circuit instances which persist quite a bit longer than the average value of 0. And that's what's being plotted underneath the thick dots. These kind of points are the fluctuation from individual instances. So what does this tell you? First of all, maybe these fluctuations can persist for a long time, and allow us to resolve them in a regime where classical simulation is hard. And at the same time, this tells us that this observable is actually useful because it's very sensitive to the underlying detail of the quantum circuit. And if we can somehow decode these fluctuations, maybe they offer you a way to do something like Hamiltonian learning and try to probe some underlying detail of the dynamics that you can't otherwise capture. So it kind of checks both boxes of this kind of quantum advantage thing that I was talking about. Okay, so now let's look at these two things in detail. First, let's look at how this fluctuation actually decays over time. So here is some nice 2D plot of on top is the average OTOG or second order OTOG here. Take another sip of water.
Is that spectrum of fluctuation specific to a particular hardware? Does every hardware have its own signature?
It's specific to quantum circuit. We do error mitigation here, so we're recapturing the ideal behavior to very good accuracy. So it's only sensitive to what circuit you run. Yeah. Okay. So otherwise, it will be very weird to claim this is some sort of yeah. So let's now look at how the scaling of this fluctuation and go, right? So on top it's a spreading of average OTOG. So this is kind of very easy to see that there's a line cone of information that propagates as your circuit runs deeper. This is nice to see, but again, also expected. But then along this line cone fringe, you see that the OTOG fluctuation, which is what's plotted underneath, has a series of peaks that propagates outward. And even on these kind of qualitative 2D plots, you see that these fluctuations persist quite a bit, right? Going from here to here, it maybe decays somewhat in amplitude, but it's really a lot of fluctuations. And more specifically, if you kind of plot the average magnitude of these fluctuations over time, and you track where this wavefront is, you see that they kind of decay like a polynomial rather than exponential. So these kind of different colored dots are the fluctuation decays, and you can clearly see that they don't generally follow a exponential trend. Whereas if you don't do time inversion, just to go forward and measure local expectation values, let's say sigma z or something, then you get the expected exponential decay, like this gray dot. So this tells you that this kind of second or this kind of OTOG quantities give you a polynomial decaying signal size rather than exponential decay. And that's important to say that these things eventually will be cheaper to run on the quantum device rather than doing classical simulation. Okay, so this covers the signal size of it, but why do we believe these things are computationally hard, right? So this is a bit of a theory thing I need to cover. So as I mentioned, alluded in the beginning, because this is kind of backward evolution creates interference effects. And our kind of intuition is that this is a long-range effect that covered whole system size, so the classical thing will struggle. But how do we kind of visualize this and say this in a more concrete manner? So let's think about how polypath works, right? So let's take the local operator B and think about its trajectory over time, right? Every time I apply a non-Clifford operation, it branches into a superposition of either 2 or 3 polys. If you have a lot of non-Clifford gates, then you have this kind of tree-like thing. The local operator becomes a superposition of exponentially many body operators. However, the time-evolved operator, these things have a complex phase. So when you add them up, they give you 0. This is why, the regular time order correlation just decays exponentially. Now let's think about what happens when you have one-time reversal. Let's go forward and backward one time. So first order OTOG. So here, what happens is that let's think about infinite temperature limit, where your OTOG essentially is a sum of the trace of all the polys plus the product of their coefficients. So this expression here. So here, you have a situation where the two polys will only contribute to the observable if they're basically identical, right? The trace of any non-identical polys will give 0, so it doesn't contribute. So you end up with a situation where you're essentially squaring a bunch of amplitudes. And these are strictly positive terms. And this carries a very unfortunate consequence that you can sort of simulate this with Monte Carlo, because you kind of destroy the sort of the sign problem inherent in quantum mechanics. But this kind of situation disappears if you start to look at the second order OTOG, where you have a product of 4 polys, because there are 4 polys in the definition. And now you can have situations where non-identical polys can contribute to the observables. All they have to do is in Hamming-distance space, they just need to enclose a loop. So this situation is called off-diagonal OTOG squared, or second order OTOG. And then there's another situation which is similar to first order OTOG, that as soon as 2 of the polys are the same, and the other 2 being same, you can also contribute. So this second contribution is what we think is classically hard, because what happens here is the polys are unconstrained. So to keep track of this, you have no recourse other than brute force expansion of the poly operators. That's just not possible, right? So this is a kind of theoretical sort of understanding that leads us to believe that this is the hard quantity. But still, you have to also experimentally prove that on a large device, this specific contribution coming from the sum of this kind of non-identical poly products actually contribute to the signal. If your 99% of your signal is dominated by these kind of boring and easy components, then that's not so good, right? So this is where we start to kind of actually look at this effect experimentally. So the way to quantify the contribution of this this kind of off-diagonal contribution to the OTOG is to destroy the interference. So what you do is in your circuit evolution, you inject a layer of random poly operators in the middle of the evolution. So what they do is they randomize the signs of the poly coefficients without changing their amplitudes. And if there were constructive interference to begin with, then this would destroy it. And by looking at the change in the experimental signal between this kind of randomly poly average version of it and the original circuit, we can actually quantify how much our signal is coming from this long-range complicated interference effects, and how much of that is more like classical Monte Carlo effects, for instance. And the result is very encouraging in the sense that if you look at first order OTOG, which is kind of, okay, what I'm plotting here in the large plot is a correlation of the signal before and after the poly injection. So the lower this number is, meaning the smaller the signal change is. So if we look at the first order OTOG, which is these orange dots or yellow dots, if you put this layer of single random polys in the middle of the circuit evolution, you have almost perfect correlation in the signal before and after, meaning that interference effects play a very small role in first order OTOG, which is what we expected because it's dominated by these Monte Carlo processes. Whereas in the case of OTOG square, second order OTOG, which is these kind of blue dots, you see that no matter where you place the polys, it almost destroyed the correlation in the signal. So you get a complete set of completely different set of numbers. So these blue dots essentially indicate non-correlation between the after the signal, in the poly averaging. So this essentially tells us that yes, our second order OTOG signals that we're measuring in the classical computer, on the quantum computer, are dominated by this long range interference effects. Okay, so all that lays the foundation why we think this hard. Let's now kind of go and take it to the best classical simulation people we have in the team. There are roughly 10 of those. So I think covers a pretty good spectrum. So when they took our OTOG numbers, the first order OTOG numbers, they were able to beat the quantum computer in terms of accuracy. So here I'm showing 3 different curves. So these are just random OTOG numbers, as a function of different circuit instances. Each circuit instance has a different set of single qubit gates. So the red is experimental data. the black, so this is a 40-qubit experiment. So you can still simulate the numbers exactly with an expensive GPU, but you can still do it. So the experiment agrees with the exact to a reasonable amount. But then you can sort of also use Monte Carlo simulation, which discard the sign sign of the coefficient of the polys, and then you can sort of capture the signal to roughly the same accuracy as experiment. So this is not good. But now, if you move to the second order OTOG, you see that the classical methods basically fall apart, right? So here you have the experiment, which is this sort of black dots. Sorry, again, the red dots, and then the black is kind of agree pretty well. And then the classical simulation, just the sort of approximate methods like Monte Carlo, just give you garbage. And we have checked many other algorithms against this, like belief propagation, other tensor algorithm methods, and none of them give you even a semblance of correlation between the exact simulation and the protocol. Yeah, go ahead.
Can you move back?
Sure.
That simulation is also classically done. So,
Yes, on 40-qubit, you can do exact simulation.
so you're comparing exact simulation of perfect qubits to experiment of imperfect qubits.
Yes.
And what is star?
So the yellow star is the performance.
Stars fail?
Stars are fading, and the stars are the best approximate classical algorithm we can find that has a polynomial scaling in complexity. So these are basically struggling against second order OTOG, but they succeed against first order OTOG. That's a message.
How do you quantify success and failure?
Oh yeah, so no. I didn't list it here. You can compute, let's say, a signal to noise ratio against the exact simulation. I think usually we define 1. It's at least you have an SNR of 1 in order to say this is actually a meaningful signal. So the classical methods basically all have SNR less than 1, whereas our quantum processor can maintain it roughly around 3 or so.
But the exact simulation is done on a classical computer, and probably that's cheaper than your experiment.
Yes, so we're not claiming quantum advantage here. This is 40 qubits. So I'm now precisely. So let me just show you the final products, if you will. So here, now we're going somewhere, there's no classical simulation whatsoever. So here is 65 qubits. So it's large enough that nothing can stick. And then we kind of sampled a lot of times, and these are still small numbers, unfortunately, but we can resolve them within statistical uncertainty. Then we get a set of numbers like this, okay? And then these numbers are on the internet. We uploaded the circuit, we uploaded numbers, kind of we're waiting for someone to manage to match this. So far, no one has done that. Hopefully, we're good for now.
Somebody with unknown source of approximation error to match your noise.
So
Imagine, they're not gonna match.
yeah. So precisely, great point. So this is what these lower plots are for. So you have to somewhat project what the accuracy of your measurements is in the regime where it's intractable, right? You can never be 100%. I mean, noise models, someone can screw up in the lab. You can never be 100% sure that it's going to be there, but we did make an honest attempt. So this is what these lower plots are meant to do. So yeah.
But if you're doing to do auto, you're running forward and backward, right?
Right.
So if the one good measure of how good a job you're doing would be you should come back to 1.
Yeah. So
right.
Oh, never. So but yeah. So let me explain the lower plots. So what we're doing is we always rescale the entire curve by their variance. So largely speaking, that takes care of the noise factor. So when we go and compare against numerical simulations, we always take this set of 50 numbers, and first thing we do is scale the whole thing by their own variance. And then we compare the result. Right. So what we're saying is the noise essentially act like a global damping factor. That is not a precise assumption. This is why our accuracy is not infinite. And that accuracy is what we're trying to extrapolate here. So let me just show you this, maybe then we can discuss whether this is valid or not. Right. So what we're seeing here is the errors you make on the individual circuit OTOGs scales roughly proportionally in linear fashion against the average signal size. So these are errors against signal amplitude.
So there's error against the exact simulation.
Yes, for 27, 36 qubits, where we can sort of simulate easily. And they kind of scale linearly, right? So this is one observation. And they're almost identical between 27 and 36. The circuit volume actually doubled from one case to the other. So let's make an assumption, and this is probably the best we can do under the circumstances. Just say that the errors are basically, I can literally fit a line to this and say, how much error am I supposed to make for each dot I have? Now let's see whether we can use to predict the error distribution for different system sizes up to the limit of 40 qubits where I can still simulate. And you can see that the error model from this empirical observation roughly covers the experimental signal to noise ratio up to the 40 qubit limit. So the best thing you can do is apply this error model to the 65 qubit and give a confidence interval for the signal to noise ratio. So it's something somewhere between 2 to 3. This is the best we can do, because otherwise, without knowing the exact answer, you really cannot say how accurate it is. Right. So if you think there are other ways to validate this to better comfort, we'll kind of welcome this. We spent several months trying to think about how to, again, this is a fundamental problem with quantum supremacy or advantage. In the regime, we cannot classically calculate how do you know the processor is doing the right job. And this is the best extrapolation we can come up with as the experimentalist.
But UTOG was originally invented as a way of measuring quantum chaos, right?
Yeah.
So it's supposed to be like, classical chaos, butterfly, diagonal exponent kind of thing. So can you, like, I was forgetting about, comparing to classical simulation or whatever, let's imagine, if I can take this as a meaningful quantum dynamic simulation, is there a way to see from your experiment, look, there is quantum chaos happening based on having a photon?
Well, you can go and try to measure entanglement entropy and see how much that is. We haven't done that, although we have classically tried to simulate what the entanglement entropy looked like in the resulting wave function out of this circuit. It looks pretty big. It's not fully random matrix limit that I can tell you. Otherwise, you just, there's kind of boring. There's nothing to measure. These things happen to, usually what you're doing, you're kind of trying to stay close to the wavefront of these things, right? So you're basically fully in a ergodic limit if you're deep within this wavefront. And you're essentially
chaotic, or
we're partially chaotic. The title of this paper is Interference in the Edge of Quantum Ergodicity. So this is right around the point where the system transitions from simple to chaotic.
But have you pushed beyond to know that the other side is chaotic?
You would just get 0 OTOGs once you go too deep in the chaotic region. So this is essentially playing a game of going somewhere in the transition region where things are classically hard, and at the same time, the numbers are not so crazily small.
Still, are already kind of small, right? So
Yeah. So these things takes people 3 weeks to average out. These are very small numbers. And this is actually the ideal value, which is already a couple %. And there's maybe 10% or something fidelity on top of this. We're dealing with -4 range. So it takes a lot of shots, which kind of nice because cold atoms can never do this, I hope at the moment. Yeah, so.
Really?
No, well, every circuit is 500 million shots. And there are 50 circuits. So this thing is billions of shots. So it takes us, maybe this is the point where I should bring stability. I think we were talking about that at lunch. So it takes maybe 100 reconfiguration and recalibration of the whole device to get this whole data set. It's a lot of work, but yeah, it's kind of there. Okay. I think I'm running out of time, so let me quickly flash. So, okay, so now we know, this is at least, we hope SNR of 2 to 3. Again, if someone manages to simulate this and can bound their classical method, we look forward to that. But so far, no one tried it or has been able to, hasn't been successful yet. So now if you take this, then the approximate methods all kind of fall flat because they all have SNR less than 1. So the only disposal you have, if you ever want to try this with a supercomputer, is traditional tensor contraction methods. And we estimate it takes, I don't know, 3 years or something to simulate each circuit on Frontier. So no one will ever try this. and we believe in this case, it's kind of the quantum computation of expectation value, not sampling problem, that managed to cross this threshold. Of course, we, again, as I acknowledged, that the classical methods are very powerful. They evolve over time, so we can never guarantee this will stay in that regime. But hopefully, as our quantum processor gets better, we can stay ahead of curve. Yes?
You probably said, what was the size of the system?
65 qubits. Yeah. Yeah. Okay. Just quickly flesh out, and then the kind of, okay, you're classically hard, but what can you use these things for? So this is very much work in progress. Is one thing that we envision using these things for is to do Hamiltonian learning. Right? Let's imagine you have one system that we can emulate is solid state NMR. So you have a series of, let's say, what they call double quantum Hamiltonian. You can actually emulate that using an XY model type of set of circuits, and you can produce OTOC or OTOC squared on your quantum device. What they can do, let's say in the NMR lab, is they can also produce the same set of numbers, but they don't have the microscopic details of all of their couplings. So one thing that we're thinking about doing is to emulate NMR systems and then try to decode what the specific couplings in your molecules are. We haven't done that Hamiltonian yet, but on the random circuit sampling, in the random circuit setting, you can sort of do a toy model where, let's say, you don't really know what the coupling between those two qubits are, and you're relying on the quantum computer to decode that for you. So you can now sort of sweep the coupling strength of this, compare that against classical simulation, and see there's a clear minimum in your cost function where the true coupling of this 2-qubit gate is. So this is where we hope to push this work into the future. So
that will be assuming you have items.
So depending on Hamiltonian, so the double quantum Hamiltonian that you use for MR is just XX minus YY. So that's effectively an XY model, but then you have to flip the spins to get the minus sign. Yeah, but that's something one can trawlerize and do. Okay. So I only have 10 minutes left, but maybe just quickly flesh out this last work, which is trying to move away from random circuits and really study some sort of physics phenomenon, which is interesting. It's not classically hard yet, we can say that, but it's moving in that direction. So I'm gonna maybe skip a bunch of things. So this work is, let's go straight into the physics. So this is done with an analog way of controlling our chip, right? So with our chip, you can sort of either do digital gates, or you can sort of turn on all of the couplers at once and let the system evolve using its native Hamiltonian, which is a Bose-Hubbard model. In the sort of small coupling regime, your system never goes to the higher computational space. So you're dealing with essentially a two-dimensional XY model with some small parasitic interactions. So this analog system is very nice because you can drive it and then you don't have to worry about heat death from trawlerization. Right? In 2D, that's a big issue. If you ever try to trawlerize Hamiltonian in 2D, it quickly go chaotic and there's nothing much to measure. So at the first step, and this is actually much driven by Trong, one of my reports. So one thing once we sort of figure out how the scheme of calibrating this analog system, the first thing we try to flesh our sort of muscles is to try to do adiabatic preparation. This is very hard digitally. But the analog wise, you can sort of do this, right? So let's say I'm interested in preparing low temperature state of the two-dimensional XY model. How would I do that? So what you can do is start a system in an antiferromatic state. So basically a Z-basis state, very trivial. And then you kind of gradually turn down the onside potential, so the local Z go to 0, and then at the same time ramp up the couplings. The XY interaction goes to some maximum value. And do it slowly enough. So you can see that as you go slow enough, you create a lot of very long-range correlations. So these are correlations in XY plane, right? So as you kind of, and this label here indicate how long the ramp is. So in 23 or something, it's very low, very slow ramp, but still fast enough to overcome decoherence because all of the couplers are on at once, so dynamics goes fast. Then we managed to reach a very correlated state, which mimics the ground state of a two-dimensional XY model. So this, when we saw this, we were kind of taken aback because usually you could only see this kind of clean plots in cold atom physics type of experiments. This is the first time when we saw, oh man, you can sort of, in solid state qubits, you can do something like this. So, but this is still ground state physics in a square lattice, a kind of, MPS or something can capture this very well. So the question is, and also people have known this for a long time, so there's no surprise there. So let's see now, can we move away from ground state physics and study something about the criticality of this model? What does that mean? So the one way to do that is sort of introduce back the on-site potential, right? So I can now sort of, in addition to XY coupling, I can introduce some on-site Z field. And if I look at the relative strength of XY coupling and the Z field, there's kind of expected to have a ground state sort of quantum phase transition somewhere in a critical field strength of H. So, so what we try to do is to try to study the critical property of this transition using the Kibble-Zurich mechanism. So what it does is you kind of run through this transition here with a variable speed. Right? If you go too fast, nothing happens. You just end up with product state. You go slow enough, you go to ground state. In the intermediate regime, the growth of correlation length actually has a linear behavior against the ramp time, or sorry, the inverse ramp rate. So this has been kind of sort of observed many times over in Rydberg atoms and earlier in other platforms, where it kind of conforms pretty well to this Kibble-Zurich theory. So when we first started doing this experiment, we were hoping to see something similar, and just see something similar to what people have observed. But what's kind of striking is we see something quite different. So first, let's look at how the correlation length changes with the ramp rate. So here is basically the correlation of correlator, XY correlator, as a function of distance. You can see that as you slow down the ramps, it goes from an exponential decay to a polynomial decay, which is kind of indicative of phase transition. And then from there, you can sort of back out what the correlation length of these things are as a function of ramp time, or inverse of, ramp time. What was kind of interesting is that the correlation grows quite a bit faster than what the sort of naive theory of Kibble-Zurich predicts. Right? Kibble-Zurich sort of predicts an exponent of 0.4 against the ramp time, whereas I think we observed something like 0.6. And this is actually reproduced by MPS simulations, so tensor networks. So one of these, I think, the blue one is this tensor network simulation. So this is real effects. And the question then we kind of ask ourselves, how do we explain this? What is going on here? So this is kind of slightly related to what I used to do here. So the conjecture we had, when we talked to Dima Vani is sort of, okay, well, maybe there's some other transition going on. They kind of play against each other. And the other transition, of course, for 2D XY model is there's kind of the well-known Kosterlitz-Dawes transition, right? So it's a classical phase transition as a function of temperature. So where you have this anti-vortex and vortex pairing disappearing across the phase transition. So because of this, and our system is never at ground state because of noise and other issues. So maybe there's maybe as we lower the ramp rate, we're both approaching the quantum phase transition and the classical phase transition. And the two things kind of enhance the correlation growth to go beyond what the Kibble-Zurich predicts. And there is a complicated plot which I always struggle to wrap my head around, which shows the trajectory of the system. Basically, it tells you that as we kind of change ramp rate, it crosses two different phase transitions. Okay, so that's just a conjecture. And there's a lot of related work on this. And there's also a companion paper, related paper from Misha's group studying roughly the same thing. So how do we substantiate this observation experimentally? So, well, because now we're talking thermalization, and then immediately you might think, okay, maybe the eigenstate thermalization hypothesis can shed some light on this. So what we're doing now is assume this thermalization around the classical phase transition is playing a role. Then I can conceivably prepare my system intentionally in a thermal state and see whether there's some sort of similarity to my state prepared using ramps, right? Because ETH basically tells you that whatever state you prepare, if the temperature is the same, you get the same scaling and correlation lengths and so forth. So how do we prepare a thermal state? So the way we do it is we kind of intentionally inject defects in the initial states. Rather than having a purely ordered ferromagnetic state, we intentionally flip a fraction of the spins, right? So this, rather than down, we go up, and we change the density of the spin flips. What it does is it basically propels your system into a different part of the XY energy spectrum and goes hotter and hotter over time. So now let's kind of compare the states you prepare using this kind of spin flips against states prepared using ramps and see whether they really look identical or not. And well, no surprise, they do look identical. So these are let's forget about this middle plot. On the right, we're looking at energy difference from the KT transition point. And then the vertical axis is the correlation length. So these dots are states either prepared using the flips or using variable ramps. You can see they kind of collapse into a single scaling function until this goes too far and the noise and stuff like that take over. But the initial rise in slope is identical no matter how you prepare a state. So this is kind of a consequence of ETH and give us the sense that thermalization is really preparing a role in the enhanced correlation growth beyond the simple Kibble-Zurich theory here. Yeah.
This ETH. Because your system is not really isolated, so it's not really an eigenstate thermalization. Right? You have external effects, you have noise,
Yeah, so no.
Question of like, why should we invoke ETH? That's one question. Another question is, it looks like the modeling is essentially by hand putting in bit flip errors. Right? Is that the right way to think?
Yeah, so the
Full experiment?
so there are a couple of things. So first of all, we kind of, this is an analog system and we can do post-selection on them. So we actually drive out noise effect to a very large extent.
Okay.
So we can verify that in at least the time scale we're dealing with, the noise plays a relatively minor role. So there's that. Now, even if there is tiny bit of noise, I think the effect on the state is essentially also thermalization. It drags it into a more sort of decoherent or thermal. It drives up the temperature.
So it is thermalization, but the question is it like eigenstate thermalization of an isolated system kind of thermalization?
I see.
Or mundane thermalization that I'm in a room whose thermostat is
Yeah. No. I think, okay, that I can answer. I think it's mostly actual coherent effects in the sense that these are not, again, like I said, so the time scale and the system scale that we're dealing with is such that the noise is not a dominant mechanism. And we can verify that with MPS simulations. They agree pretty well with those things. Which, MPS is for this kind of temperature scales is usually pretty accurate. Does that kind of answer? I'm not exactly sure with that.
No. You have to somehow get to your ground state. Your system somehow, if it is analog system, right? The analog system has to somehow cool, right?
That's done by the variable ramps, right? As we slow down the ramps, we get closer and closer to ground state. And so we can now change the temperature either through the ramp rate, or we can keep the ramp rate constant, but change the initial state to specifically target a different temperature region of the X-ray model. And the consequence of two methods is actually the same. You get the same correlation growth against energy. So that tells us something that thermalization is playing a role in this departure from Kibble-Zurich theory. So that is a qualitative argument out of this.
The phase diagram that is like DEMA, we credited DEMA to, that had a real, like, yeah, I don't know. I don't know why if it is, I guess, the thermalization, like, is that temperature same as the T in your phase diagram? Maybe why, I don't know.
So maybe the eigenstate word, the word eigenstate is probably confusing you. So all we're saying in the thermalization is
Thermalization, if you drop.
okay, fair enough. So I think maybe this is just I'm not a theorist, so some of these noises are not really, maybe I'm not so differentiating between those things, but anyhow. So that is a sort of the kind of theoretical picture, at least I have in my mind, is how this corroborates that picture. So I think I'm almost out of time, but also I'm at the very last slide. So analog systems are very cool because now you can study other things as well. So the previous things are nice, but then again, we're talking about low temperature physics. So these things are classically simulatable. So one thing we're trying to do right now is combining our digital capability, where we can prepare sort of digitally entangled states and analog evolution to see whether we can study like microscopic details of transport, for instance. So here is kind of a set of nice pictures showing how energy or spin moved across the lattice if you create an imbalance and stuff like that. So these are so far just nice pictures, but one focus within my team is to try to understand the computational complexity of these transport sort of problems and see whether there are some temperature regime and some sort of quantity that we can do that tells us something about transport properties at the same time it's hard to classically simulate. And I think that's rush time. Okay, so maybe time for questions, I don't know.
I No questions or too many questions?
Right, I don't know whether it's because it's all clear or it's just like too confusing. All right, hope it's a. Okay, well,
All right, let's
Cool.